Welcome back to Rust coding challenges. Today a classic, merge two sorted linked lists into one sorted list. The algorithm is a simple zipper. At each step, take the smaller head. But in Rust, there's a real lesson hiding in it. How do you splice two heap-owned lists together without cloning a single node? The answer is a neat ownership dance the borrow checker actually loves. We'll build it recursively in about 10 lines and run it. Let's go. Here's the setup. Two linked lists, each already sorted. We want one merged list, still sorted, and ideally we reuse the existing nodes rather than copying them. The idea is a zipper. Look at both heads, take the smaller one, and repeat. Easy on paper. The Rust twist is ownership. Each node is a box that owns the rest of the list behind it. So to stitch two lists together, we have to move that ownership around carefully, one node at a time. There's the zipper in a picture. List A starts 1, 3, 5. List B starts 2, 4, 6. Compare the heads. One is smaller, so one goes first. And now we merge the rest of A, 3, 5 against all of B. Compare again. 2 is smaller, 2 goes next. Then 3, then 4, and so on, always taking the smaller head and recursing on what's left. Each comparison places exactly one node, so the whole thing is linear in the total length, and we never copy a node, we just relink them. Let's build it. A list node holds a value, and on the heap the rest of the list an optional box. The signature is the whole story. Merge takes ownership of both lists, an optional box each, and returns one merged optional box. Taking ownership is the key. It lets us move nodes from the input straight into the output. No copying. Below it two little helpers to build and print lists, and a main to try it. Now the body. Here's the whole algorithm, and it's a single match on the pair of lists. If either side is empty, the answer is just the other side done. Otherwise, we have both heads, na and nb. If a's value is smaller or equal, we keep a's node. We set its next to the merge of the rest of a with all of b and hand it back. Otherwise, we keep b's node the same way. That recursive call is where the magic is. We move the tail of a and the whole of b into the next merge. And Rust's ownership rules make sure every node has exactly one owner the entire time. No clones, no null pointer bugs. The compiler simply won't let them happen. Let's run it on list A 1, 3, 5, 7 and list B 2, 4, 6, and there it is 1, 2, 3, 4, 5, 6, 7, one clean sorted list built by relinking the original nodes in place. The two input lists were consumed, their nodes now live inside the merged one. Linear time, constant extra space beyond the recursion, and not a single copied node. That's why it's clean. Every comparison commits exactly one node to the output, so the work is the sum of the two lengths linear, because we move boxes instead of cloning them. We use no extra heap at all beyond the call stack. Matching on the pair of lists takes ownership of both, and the empty list case is the base case that stops the recursion. And the part you get for free in Rust, because the ownership is tracked, there's no way to leave a dangling pointer or free a node twice, the exact bugs that make linked lists miserable in C. The compiler proves it for you. Quick recap. Merging two sorted lists is a zipper. Take the smaller head, recurse on the rest. In Rust, we express it as one match that moves the boxed nodes. So we relink instead of copy, linear time, constant extra space. And the real takeaway, the ownership model that makes Rust feel strict is exactly what makes this pointer splicing safe by construction. Fight the borrow checker once and it hands you correctness for free. A quick note, breaking these algorithms down in Rust line by line takes real work. If it helps you, the wallets are on screen and there's a Ko-fi link below. Every tip funds the next one. Thank you. That's merge to sorted lists, a recursive zipper that relinks nodes by moving ownership, with the borrow checker guaranteeing there are no pointer bugs. Subscribe so you don't miss the next challenge. Tell me in the comments which problem to break down next, and I'll see you there.